Okay, hello everybody and welcome to this webinar on process failure mode and effects analysis and control plans. My name is Ian Riggs and I'll be leading you through this for the next hour and a half to 2 hours, and also being able to answer any of your questions. So just for everybody's information, we are recording today's session, and this will be made available on the AESQ website in the next 2 weeks. We will also provide a copy of the slide packs we've been using on day 1, day 2, and today's as well. You will get an email telling you when it is available on the website with a link of how to get access to it. So this is the third session, and today we're going to focus on something called Reference FMEAs. So I understand that when we went through session 1 and 2, the scope of the FMEA might be much broader than you're used to doing. Reference FMEAs is one fantastic way of making sure we do that efficiently, that we use knowledge that we've gained from other processes and other part numbers to carry that forward, which improves the effectiveness of the FMEA because it's our best knowledge of how to make that part, but also drastically reduces the time needed for engineers to actually score and create the risk profile and therefore complete the FMEA. So in the first webinar, we looked at what are the hard requirements in 13100, and also we gave a high-level overview of what the Process FMEA needed to address. Yesterday, we went through the FMEA in much more detail, step by step, showing you the intent of each of those steps and some of the common pitfalls we see when we review FMEAs today. Today, we're going to start in a moment and look at reference FMEAs and how they can help. So just a little introduction to myself. If you weren't on the earlier WebExes, my name is Ian Riggs. I'm the Quality Executive for Civil Aerospace for Rolls-Royce based in Derby. And prior to joining Rolls-Royce in 2005, I had about 16 years experience working in the automotive industry for companies such as Cosworth, who did high performance engines for Bentley, Audi, and Volkswagen, as well as a company called Harman International that does automotive in-car entertainment based out of Indianapolis. In 2013, I was one of the founding members of AESQ, and I was the inaugural chairman, which I've done twice. So I also did 2019 to 21. But I was also the team leader for 13100 development and 13003. If you know what that standard is, it's all about measurement systems analysis. And I'm also currently the team leader for the reference manual 13004 defect prevention tools, and that's where FMEA and control plan sits. I'm also getting some great support from my colleagues today, Becky Lemon and Rudolph Brownreader from MTU. So Becky, can I hand over to you to explain how the polling is going to work and maybe a short introduction?
Sure. So hello, everyone. My name is Becky Lemon. I'm the Industry Program Manager at the SAE Industry Technologies Consortia and the Program Manager for the AESQ. Today, we are going to use the Slido polling feature again for a couple of more polls to make it a little more interactive and interesting. So we hope you will engage with us today. Thanks.
Thanks, Becky. And Rudy?
So, yes, good morning, good afternoon, and good evening in some countries. It's Rudolf Braunrieder from MTU Aero Engines in Munich again. Third and last day of the webinar, and also today I will handle your questions and comments. So I already had a lot of fun with your comments just before. So please use the chat function for this purpose. As usual, I will collect your questions and Ian will answer them during the provided period. Same procedure as yesterday. So thank you and have a successful webinar.
Thanks, Rudy. And any questions we don't get to answer during the session, we are collecting all of those in, and we will provide answers and post those on the website as well. So that's who we are. Now to cover who you are. We've been really, it's been a fantastic response from everybody to take the time and come along to these webinars this week. We've had over 700 people have registered from over 250 companies in 27 countries. So as Rudy said, we have some people who are just waking up, some people are just going to bed, and everybody else in between. So I know how busy everybody is. I really appreciate the time you've taken to learn a little bit more about the AESQ approach to FMEA and control plans, and hope you find it useful. And just to give you a taste of who is in the room, I haven't got all 250 logos on here, but you can see we have airframers, our customers such as Airbus, Boeing, Lockheed Martin, Sikorsky. We have all of the engine manufacturers that are members of the AESQ, and a whole range of different suppliers from all over the world. So thank you very much for joining. And as I said, I hope you find it really useful. So in today's webinar, I'm going to explain what we mean by a reference FMEA. You may know it by some other terms. 25 years ago when I was in automotive, the term unit FMEAs was one that was used quite a lot. So I'll explain what we mean by a reference FMEA. And then I'm going to walk you through the steps of how would you go about creating a library of reference FMEAs that you can use as building blocks to create your part-specific FMEA later on. We're then going to take a look at control plans. Control plans are in 13100. There's a few specific requirements we're going to look at, but more importantly, we're going to show the link between the process FMEA and the control plan, and how much of the control plan information is actually taken directly from the FMEA. We're going to have some time at the end for questions and answers, but we will split up at the end of each of these sections to give you an opportunity to ask questions. And as Rudy said, if you can send in questions at any time. I've noticed before we even started the presentation, some questions had already come in, so I think we're getting the hang of using that chat function. So hopefully we'll be able to answer most of those as we go through today. Now, just to point out, I know we're focusing on process FMEA and control plans, but it's important to realize these are part of a system. And there's inputs and outputs from both of these tools. Within APQP in particular, how these tools fit together is really important. We have a great video that we produced. It's available on the AESQ website that shows how each of these tools fit together, where they are in AS 13100 or which reference manual applies. You can view it on the website. You can download it and use it within your own organization. We can't show it on WebEx, unfortunately, but it's the link. If you click on the AESQ link, you'll be able to find that very easily, and hopefully you'll find that very useful as well. So let's begin with, what do we mean by a reference FMEA? So if you take this example, this is a process FMEA. It's at Op10. It's a CNC drilling operation. And you can see in the requirements column, we've selected two features that we are creating. We are creating a fuel hole with a 50mm diameter, and we are creating a water hole with an 80mm diameter. It's got the tolerance on there as well. As you go through then, and we've only selected some of the failure modes and effects just to illustrate this, but if you go across from the fuel hole, how can you get a diameter wrong? Hopefully you know from session 1 and session 2, it's too big or too small. So irrespective of the fact one is a fuel hole and one's a water hole, and one's 50mm and one's 80mm, the only ways you can get those failure mode for a diameter is too big or too small. So for both fuel and water, failure modes are the same. The effects, some are the same, but some are very different. So for instance, fuel hole, if it's too big, could cause a fuel leak. Worst thing that could happen, you could have an explosion. So the severity for that has been scored as a 9. Because it's too big, then scrapping the part may be an issue. If the hole is too small, you might be able to rework it, and that has its own severities. But the difference is, if it's a fuel hole and it leaks, you get an extreme event, scores a very high severity. If it's a water hole and it leaks, then it's much more benign. It's not going to cause such a severe reaction, and therefore this one has been scored severity 6. It also has the potential that you need to scrap the part if the hole is too big, or rework it if the hole is too small. And as you work across, now that we've got, well, what could cause that hole to be big? If you look in your potential causes, for fuel hole, oversized tool, spindle alignment error are 2 of the causes, and they're the same causes for the water hole. The prevention controls for oversized tool, spindle alignment, excessive drill wear are exactly the same if it's a fuel hole or a water hole. The detection controls are the same, etc. Now what you'll notice, the occurrence scores are different because the tolerance on the fuel hole is a lot tighter than the water hole. So the occurrence score for the fuel hole is higher, because if you imagine, the capability is not going to be as good as if you've got a plus or minus 1 millimeter specification. So again, the occurrence scores are different. And because the fuel hole has such a high severity, you may choose to do a different detection method, and you may get a different detection score. So the point I'm getting to really is, if you're doing a CNC drilling operation, it doesn't matter what type or what the purpose of the hole is. When it comes to diameter, there are some things that will always be the same, irrespective of hole dimension, hole tolerance, purpose of that hole. So the failure modes, causes, prevention controls, detection controls will typically be the same wherever you have a diameter created by a CNC drilling operation. The differences or potential differences come in on potential effects and the severity, because the fact that one hole is used for fuel and the other one is used for water may lead to a different consequence if it was non-conforming, and therefore a different severity. The occurrence will be different because the specification is different, and therefore the capability of the process is different, and therefore the occurrence score you would expect to be different. And potentially the detection score will be different depending on what you actually do to create it. And it might be that for plus minus 1 millimeter, we have a capable measurement method, but it's not capable at 0.2, and therefore you're going to get a higher score because you haven't established MSA for that. So if we understand that, what we can actually do is say, well, how do we take advantage of knowing, once we've done an FMEA on fuel hole diameter, on hole diameter, all of the text that's in blue on there we could use again. So every time we are considering a hole diameter, the bits that are always the same, we can cut and paste and use. Essentially, that's what a reference FMEA is. So for a drilling operation, on here you can see that on any drilling operation, what are the typical requirements that might get called up on a drawing? So you've got diameter, position, roundness, depth, no FOD, straightness, pitch. If we identify all of the different requirements, in other words, in this case, all of the different geometric tolerances or characteristics that you'd be asked to create, we can create the failure modes for each of those characteristics. And as we saw yesterday, failure modes are finite. There is only so many ways a diameter, position, roundness, or depth can be non-conforming. For a CNC machine, if you say, well, what could make depth too deep or too shallow? The potential causes will be the same for any hole that you're drilling when you're considering depth. So once we identify that list, again, we can reuse that. The prevention controls we have are typically what an organization is used to doing. So if you're doing it on one part number, such as, I don't know, if you always use air detect on your fixtures to make sure the part is in the right place on the fixture, you would do that on all of your parts so you can copy across prevention controls. And the same with detection controls. So a reference process FMEA is a way we can use the knowledge that these things will always be the same, and irrespective of the requirement, we can just cut and paste that. So the aim for us is to create a library of reference FMEAs. So in this case, here's some examples. So a CNC drilling process or milling process, inertia welding, chemical etching. For each of the processes you use to create your product, if you were to take that approach and create a reference FMEA, you're going to be able to use those as building blocks when you actually come to produce a part-specific FMEA. And we'll show you how they come together in a moment. So on part 2, we're going to lead through, well, how would you go about creating a process FMEA? And whether you're doing your first ever FMEA or you have to do 50 FMEAs, I would always recommend you start with breaking down and identifying where the reference FMEAs could be used. So let's actually look through and actually try and create one. So step 1, we've got a process flow diagram. We've got a grinding operation, a turning operation, drilling, welding, storage, assembly, and packaging. So let's start with one of those processes and focus in on it. So we're going to pick CNC drilling. The second step is for CNC drilling, what are all the characteristics that we will be asked to create on that process by the engineering drawing? And as we said just now, it's things like diameter, hole position, hole depth, roundness, straightness, etc. We would create a list of everything that is on the drawing. We might use the characteristic matrix to help us with that too. Once we have that list, we can start to work through it. So in this case, let's start with hole diameter. So step 3, for each of the characteristics identified, we're now going to look at what are the failure modes for that. So hole diameter, we said it could be too big or too small. This team has actually included not present as well. So you may get a situation where if the drill was to break, there is no feature because it was a missed operation because the drill had broken. So one of the failure modes could be not present. Now that could be a failure mode on its own. We've listed it under hole diameter. But as I said, these are finite. So you could go through all of these: hole position, hole depth. There's only so many ways in which that could fail. So this one, we'll work it across to step 4. We're going to choose hole too big. And for hole too big, we've identified what are all the causes in that CNC operation that could cause the hole to be too big. In this example, we've got the drill is oversized from the supplier. Spindle alignment is not true. The drill gets damaged in some way. The part is loose in the fixture. We've got a swarf trapped in the hole or on the drill. And we would do that then for all the failure modes. So for too small, we would have a different list for what are the potential causes. If we choose spindle alignment error, the next one is to say, well, what is the prevention control that would prevent spindle alignment error? And in this case, we've got one called machine calibration or preventive maintenance. So that is one method we have to try and prevent that spindle alignment getting out of tolerance. But we also have a detection control, which is we're going to do a ball bar check every week to see if the spindle alignment is still within specification. But we've put that under detection controls. Next on the detection controls, the other thing we do is actually measure the part so we can validate is the hole diameter in spec or not. And for that, we've got an inspection method, CMM measurement at op 250. So once you've created that, you would work through the other characteristics, the other failure modes, the other causes, etc., and develop the reference FMEA for CNC drilling, and then you go on and do your other processes. But once you've done it, whenever you're looking at a CNC drilling operation, you can pull this reference FMEA out and select the bits you need to go into your part-specific FMEA. Now, what you need to do then to join it together, you would have your process flow diagram, your specifications in your drawing, and you would start, as you can see here, to populate what we call a shell FMEA. So shell FMEA is your list of reference FMEAs joined together in the right sequence with the right characteristics listed on it. And normally you would do that, clearly using some PFMEA software, but it combines the library of reference FMEAs to either your characteristics matrix or your process flow diagram, etc. And when it brings it together, it's giving you an FMEA with all of the characteristics listed in sequence by operation. The only things that aren't completed are the effects, severity score, occurrence score, and detection score. Everything else is taken from your reference FMEA. Now, in Rolls-Royce, we had an office out in Bangalore full of really clever engineers, and they developed a piece of software that, using the reference FMEAs and the characteristics matrix, could actually bring this together in a matter of minutes. And if anybody was at the East Hartford AESQ Supplier Forum a couple of years ago, you'd have seen the video of the team doing this. The other extreme, if you had all your reference FMEAs in Excel, it would mean somebody having to work through and effectively copy and paste from the reference FMEAs into your shell FMEA. But if you've got the right software, you can create a really simple program that will do that automatically for you. So then what you would have, when you bring your cross-functional team together, the starting point is not a blank sheet of paper. It's not a sheet of A3 with a ruler. What you actually start with is a document called a shell FMEA, which has all of the information you need on it, except for the effects, severity, occurrence, and detection. Now, there may be things in the reference FMEA where you need to tweak it because there's some uniqueness with the part that you're considering. Maybe the reference FMEA has things in it that don't apply to the part that you're looking at, or the reference FMEA doesn't take account of something that's unique about the new part you're looking at. But if you consider how Rolls-Royce did this with the Bangalore team, the first meeting of the cross-functional team to develop the part-specific process FMEA, they'd be presented with this as a document for the whole part, every operation, all the requirements, the failure modes, causes, prevention controls and detection controls already completed. Now what the team need to do is go through it line by line and say, right, so what's the effect? If this hole was too big, it's a fuel hole, therefore, what's the effect? I know the effect, what's the severity? That's where you would bring your designer in to answer the effects and severity column. Okay, and you can work through those. And you know, some organizations would work that down the list with the design resource they have, to maximize the use of the design engineer, but also if they do find any severity 1 scores, they know they don't have to do anything else to the right. Okay, but effectively what the team are doing is identifying the effects and then using the scoring criteria to rate the severity, occurrence and detection. So clearly to do the occurrence, you know, it's not as simple as just looking at the table. You need data to tell you, well, what's the CPK of that process, or how often does the spindle alignment go out of calibration, so you can actually do that scoring. So there's information required to allow the team to score this. But now that's all they're doing. They're not trying to create what are the failure modes for this particular requirement, because you've already decided on those. It's not going to look at trying to identify all the potential causes, because you've already got those in the reference FMEA. So that's, if you look at it, what the cross-functional team are doing is the stuff that's in red. Everything else, if automated, and if you've created the reference FMEAs in the first place, will be done in a matter of hours. So how long does it take? I'll speak from Rolls-Royce experience. So to create a reference FMEA, when we did this in Rolls-Royce, we used this as a bit of a learning exercise. So many of the first workshops we did had 20 people in it, because we were learning how to create a reference FMEA. But in practice, you've got a team of 3 to 5 people, some process experts, the maintenance guy, maybe an operator, or certainly somebody from manufacturing. And with that small team, you're going to go through a specific process and create that reference FMEA. Normally, that should take around 30 hours. From our experience, you know, whether it was a welding operation, a machining operation, an assembly operation, 30 man hours using 3 to 5 people is how long it will take to create that reference FMEA that you're going to put into your library. You will need a reference FMEA for every process that you have. So when you look at your process flow diagram, you know, your CNC machining, your assembly, your welding, your coating processes, etc. For each type of process, you will need a reference FMEA. And we've also found that actually, even though we have multiple CNC operations across Rolls-Royce, the way some CNCs are built means that it'll have different ways of failing to cause a failure mode. So in some cases, we might have 2 CNC reference FMEAs for drilling, let's say, because the structure of the CNC machine is different and the potential causes are therefore, in some cases, unique to a particular type of machine. So you're going to kind of have to work through that. But once you've got a reference FMEA for each of your processes, you're going to use those over and over again. Then to create the shell FMEA, well, you've got 2 ways of doing it. You know, let's say you've got everything's in Excel and some poor soul has to go through and manually cut and paste those things in. You're probably looking at 30 man hours to do that, to create it for a part. And this is for a part with about 1,000 characteristics. Okay. But as I've said, if you're using dedicated software, there's a potential that you could reduce this much further. And you know, I've allowed an hour. The video that we showed back in Hartford of the Rolls-Royce Bangalore team, it actually took 5 minutes. So selecting the right software, having the expertise to actually combine these different tools, whether it's a characteristics matrix, process flow diagram, and the reference FMEAs, can really automate this. Then once you've got the shell FMEA, this is where that cross-functional team comes in. Now you're talking about a specific part that's going to be used in a specific way. And now you're going to create your part number specific FMEA. Using the shell FMEA, this is very similar to what we talked about the other day. The first one will always take longer because you're going to go through a learning process with that team. It'll take 4 or 5 before you've actually got the experience to really hone how long it takes. But you know, you're talking, you know, less than 100 hours for a part with 1,000 characteristics. As we said the other day, we will be building these parts for maybe 20, 30 years. So the investment up front in doing this will pay back. And what we've seen and the examples of the suppliers who presented at the supply forums have shown, you can actually make a step change, not an incremental change, a step change in quality performance as a result of using FMEA, changing your process to take account of that, introducing mistake proofing or statistical process control on those things that are marginal capability, and maybe having more leeway in how you control things where the capability of the process is much better. So the other benefit we've seen, when you do this at the right time in the process, so if you can be doing your Process FMEA at a very early stage when the design is still being developed, you can actually use the FMEA to say, well, I know that's how we used to design our fixtures, but the FMEA is telling us we need to do more mistake proofing on the fixture. We need to invest in maybe air detect, or we need to invest in some mistake proofing to make sure that that the part is going to be held securely, etc. Once you've done the FMEA and it's too late, you've already spent your money, it's going to be very difficult to convince your organization to go and invest in new fixtures, new tooling, etc. So this is a fantastic way of actually cutting down the amount of engineering hours it will take to do your reference FMEA. But it's more than just a cut and paste, because those reference FMEAs, if we keep them up to date, we'll have all of the latest knowledge from how we make that part. So the quality of the FMEAs will be built on all of that learning, all of that read across from all of the different things we've seen on every part we make. So it isn't, you know, just using information and then just ticking some boxes. It allows the engineering time to actually go through and say, well, so what? What are we going to do with this risk profile to de-risk it? Okay, so it is important we do it really early in the process. It does come with, you know, you might say, yeah, but the design, if it iterates, you've got to redo the Process FMEA all the time. It shouldn't be big changes, because I guarantee it, when we come to CNC machine a bearing housing or a turbine blade, the fundamental process is the same. It's the detail of fixturing, of tooling, of cycle times, of coolant application that will change. You know, so any changes to the design will rarely fundamentally change how it is you're going to actually make the part, but it's how you optimize the process as a result of your Process FMEA. So for Process FMEA efficiency, you know, I always get the sharp intake of breath when we talk about it, but it's every part number going forward as part of NPI and process changes needs a part-specific FMEA. It must have every process step, and it must have every characteristic in it. Normally that makes people think, well, hang on, this is just too big for us to cope with. But if we use reference FMEAs and we use the right type of software, we can actually reduce this to a optimum number of hours to use that engineering time really wisely. And when we used to roll this out in our supply chain and within Rolls-Royce, you'd say, well, how many hours do you think this part, how many hours are you prepared to invest in a process FMEA? How many man hours? It's 300, 400 hours, but no more than that. Well, here's the way we've demonstrated where we can actually get it to less than 100 hours in most cases. The other thing that we've learned is sometimes, when you're faced with starting this FMEA journey, the teams can spend a lot of time about, well, where do we start? What's the process we're going to start on? The part number we're going to start on? In some cases, we've seen more elaborate plans about where to start the process than just getting on and doing it. So there's nothing more valuable than getting the team to actually have a go and start to develop your reference FMEAs or start to use them to create your part-specific ones. Don't waste time talking about how you're going to plan to do it. Get the teams, the earlier you can get the teams to start using it, there will be teething issues. That it's all part of the maturing of the engineering knowledge to how to deal with it. Get the team to have a go. That's where the learning will happen. And it can be really tempting for shortcuts. It can be easy to say, well, we're not going to do all characteristics, or we're going to group these parts together because they all kind of look the same. That is not where the benefit lies of this approach. And the worst thing that can happen is we spend the next few years rolling out FMEA and the organization doesn't see any benefit. If we don't do it with the right intent, we're not going to get the results, and the organization will come to the conclusion this stuff doesn't work. And that would be a real shame, because the automotive industry has shown over the last 30, 40 years what a game changer process FMEAs and advanced quality planning was. We need to catch up, and we need to be on that journey. And from Rolls-Royce as a customer to Airbus as our customer, we will only be successful if all of the 70% of the parts that come into a Rolls-Royce engine from the external supply chain actually go through this level of rigor, and we don't get the pop-up surprises, and we don't get the quality issues that we can sometimes get. So it's a team sport. We need help from our customers. We need to help our suppliers. Our suppliers need to help us. Don't take the route of shortcuts. Plan for how do you do FMEAs with the right intent as described in 13100 and in RM 13004. Okay, section 1 complete. So Rudy, do we have any questions?
Yes, Jens, I have received a couple of really good questions. So just let me see. The first questions that has arrived is, at what point should we formally start creating the PFMEA on an NPI program, on concept design, draft drawing, or final issue?
Yeah, so on day 1, we showed a map, an APQP map. And in phase 2, the design FMEA or the design work begins. And when you look at the sort of timing chart of things that are in phase 3, which is the production method design, you'll see that the PFMEA starts pretty much at the same time as the design FMEA. And the reason for that is, I think everybody is probably on the call saying, well, if design hadn't done that, this would have made this much easier to have made. They've chosen tolerances I can't meet. They've designed a material that is really hard to get hold of or hard to process when there's other equivalents that they could have done. If only I was involved in the design stage, then we could have ended up with a better solution. It's very rare when we've done sessions like this with Rolls-Royce suppliers that the discussion around why didn't you involve us earlier? So APQP, whether it's 9145, RM 13145, or the Automotive Blue Book from QS 9000, all say that your process method design starts at when you're starting to design the product, because it needs to be a conversation between the design team and the manufacturing team to make sure that design take account of process capabilities and also measurement capabilities, so that you can start to influence that. We had a classic example once when that came to light actually when we were doing our zero defects training. And the manufacturing engineer said, well, we've always struggled to get good MSA on this particular feature because it's quite flexible. And the drawing doesn't allow us to use any fixturing, and therefore it's almost impossible to pass MSA. And it just so happened that the designer of this part was in the same session, and he said, well, I'm not sure why you're worried about it, because that hole that you're trying to measure is only there so we can get the borescope in the engine, and to be honest, it could be plus or minus an inch. So the manufacturing engineer said, well, but the drawing tolerance is, plus or minus 2 millimeters. And the design guy said, yeah, well, that's the kind of standard drawing tolerance we would use for this type of feature. If we'd known you needed something else, we could have put it on. And as I said, it could have been plus or minus an inch, wouldn't have made any difference. The fact that that discussion didn't happen at the time of the design was an opportunity missed, because this manufacturing engineer had spent the last 2 years trying to design a measurement method that would actually pass gauge R&R. So that's why it's important it happens early. And I think I saw some of the chat that came up. So, one of the concerns is, yeah, but then you're going to have a design change. Hopefully the design changes for the better to make it easier to make. But if you're using reference FMEAs and things, bringing the FMEA up to date, it's worth investing the time up front to make those changes, because you're going to end up with a design that you can make because design have listened to you. The example we had of GK and Newington making a fan case with 4,000 or 5,000 characteristics on it, never been made defect free ever. Fan case with that many features on it, always had some level of concession or rework, so the fact that that was actually made defect free at the first article was because that design ME collaboration started working at day one, and using the information informed by the FMEA, informed by current process capabilities and measurement capabilities, was built into the design. So yes, I think if you look back at historical, how things have worked and how the behaviors have been, that might seem like a big leap of faith to say, well, that's going to happen when we go forward. But that's where we need to have those conversations. We need early collaboration. We need to be driven by data and information, and the FMEA provides us with that. But absolutely, as soon as you say, I'm going to make something that looks like this out of this material with these sort of dimensions, that's when the process design starts. That's when the process FMEA needs to start too. Okay, Rudy?
Okay, Ian, thank you. So next one is more a comment or a concern you just mentioned before. So we have concerns with the amount of administration we would need to keep the PFMEA updated with every drawing release.
Yeah, so when I read that comment, I thought it was every drawing release during the NPI phase. So if it is during the NPI phase, I would expect iterations and updates to the FMEA, because that's goodness, because hopefully you're capturing the improvements that have come from improving the design to make it easier to manufacture. Post entry into production, hopefully you're not going to see a load of design changes. But no, we know that happens from time to time. As we get service data from engines that come back, it might make us look again at different materials, different tolerances, etc. Using the reference FMEA approach, we should be able to cut down greatly on the amount of administration needed to be able to update our FMEAs. I've seen it used really effectively. There was a software system called Powerway, which was created back in the 90s, and I think it was an offshoot of GM, Ford, and Chrysler. When they launched QS9000, there was a integrated APQP package that used something called unit FMEAs, which were equivalent to what we've seen here as reference FMEAs. And if you change one reference FMEA, let's say it's on milling process or assembly, with some new knowledge, you could choose to say, right, update all of my FMEAs with this new change and the new scoring, etc., and flow that out. So everywhere that had used that reference FMEA would get automatically updated. Now, we'll come on to software a little bit later. But again, the trouble will start is if there's a change and we don't do the evaluation of, well, what's the risk? And if there is a risk, how do we mitigate it? We can end up with much bigger problems. So that's why APQP, which includes PFMEA, should be done for every engineering change, drawing change, every process change, and every source change. Because I'd say 7 out of 10 major issues we have with quality on a run-in production part comes from change control. The drawing changed, but it wasn't introduced correctly into production, and we end up with a problem because it wasn't managed correctly. So any type of change will attract the attention of our customers, attract the attention of Rolls-Royce onto its suppliers, because it's seen as a major risk area where bad things can happen. History has shown us that if we don't control changes, then bad things can happen. So we would expect FMEA to be done with the same level of rigor on a change as for new product introduction. Okay?
Okay, Ian, thank you very much. Maybe another question was, what do you do if the process flow of the shell FMEA changes? Do you adapt all part number specific PFMEAs?
Yeah, so the shell FMEA is part specific. So what the shell FMEA is, if you're making part ABC for Rolls-Royce, you have looked at how you're going to make the Rolls-Royce part, and you've selected the reference FMEAs you need to create the shell FMEA based on that specific part. So think of the shell FMEA as the first starting point of a part number specific FMEA. It's just not complete because you haven't got some of the columns filled in. So if the part that you're making for Rolls-Royce changes, obviously your shell FMEA will change. If it's an existing FMEA, it stops being a shell FMEA because you've actually filled in the rest of it. So you've got a complete part-specific FMEA for a Rolls-Royce part number. There's been a change, you would need to go in and edit it. It might be that we've added in something which is a new process step, so you'd need to select something from your Reference FMEA database and include a new step within it. Or it could be just a change to an existing element within the part specific. But clearly, if you change your process, you need to change your FMEA. Your shell FMEA it's like a caterpillar and a butterfly. If the shell FMEA is just the early stages of a part number specific FMEA. Hope that makes sense.
Okay, Ian, thank you. To software for PFMEAs, you're coming later, I think.
Yeah, we're going to talk about software a little bit later, and
okay,
it's also an area where I'd be interested to know who's using what on software, because my experience in Rolls-Royce, we use one particular type of software. I'll talk a little bit more about that later on, but I'm also interested to find out what everybody else is using.
Okay, Ian says a basic request to provide an example of an assembly FMEA. It seems more difficult compared with a machining process.
Yeah, and you're absolutely right.
That?
It is more difficult than a machine process, and the difficulty comes not from potential causes and prevention controls, etc. The difficulty comes on how we define the requirement. So if you download RM 13004, in the appendices, there are a couple of pages of an example assembly PFMEA. But you know, it's one of those areas where if that was felt to say, well, I could do with some more different types of examples on assembly, that would be really good to capture as our group. So Rudy and I can take back to the subject matter interest group and say, right, we want to create some more examples to share. So there is a current example. It's in the appendices of 13004. But you're absolutely right. Compared to a machining operation or a welding operation, defining the requirements, we need to be really careful, because I think we saw the other day when we looked at the example was material processing. If you write the requirement incorrectly, you can end up with a failure mode that isn't actually product specific. And a lot of the assembly FMEA problems I see are where the requirement leads us to define a failure mode that is not describing the product. So what I would say, you know, the other good source of information for that is if anybody's got the blue book FMEAs from the automotive, there's a fully worked example of an assembly FMEA in there too. But yeah, try 13004 as an example if you want more information, and I think that is one area that is worthy of more examples and more discussion. Then please feed it in to the subject matter interest group on the AESQ website.
Okay, thanks a lot, Ian. That's it.
Okay, thank you. Thanks, Rudy. Okay, so control plans. When you look at the requirements in 13100, there's probably half a page of requirements, but the control plan will evolve over time. So the first time you see a control plan, it might include controls which are almost, you know, as part of the development process and is going through before it becomes a production control plan. So when you look at, you know, what is it we're trying to do with this control plan? Oops. So the way I always think of a control plan, if I went to an operator in a manufacturing cell or an assembly fitter, And I said to them, what checks do you do to make sure the part is okay when you're making it? He should be able to say, well, I check this feature as a first off. I then check these on the CMM. These are the inspections I have to carry out as part of my process when I make this part. So it should be almost like a summary document that he can point to say, when I make this part number on my shift, these are the checks I need to do to make sure that my process and my product is conforming. So there's two things in it. One, it should include what are the product checks you're going to do at this operation. So if I'm in Op 10, as we saw earlier, and I'm machining a part, but it doesn't get measured until 450, the control plan for Op 10 is not going to include the measurement of the features I just created. It might include check coolant strength, or it might include check the temperature of something. But it's only the checks at that stage would be in the control plan at Op 10. There'd be a separate control plan for Op 20, Op 30, Op 40. But it's a summary document. Now, one of the problems we sometimes see is they say, yeah, we don't have control plans. They say all of our checks are in the operator instructions. And then you find the operator instructions is a big 30, 40 page document that is used for training, but never referred to again. And you ask the question of the operator, of the fitter, what checks are you doing? And you're lucky if you get maybe 10, 20% of it. So the control plan is a summary document of the checks done at a specific operation. Those controls should be taken from the preventive and detection control columns on the FMEA. Okay, and we'll show that in a moment with some examples of, because not everything in prevention and detection controls will go on your control plan, but which ones should do, we'll cover in a moment. The focus of a control plan, if we can control the inputs to the process, then we should get the output. So although it should include the physical check of the product, if we know there's a correlation between process parameters, then checking the process parameters are correct is a really good way of controlling the process to make sure we get the right product outputs. Like with the FMEA, the focus should be on prevention rather than detection. So the more things we can do with error proofing to take the onus away from an operator or an inspector to actually catch something, then that's where we should be trying to focus. And like we saw with the scoring yesterday on detection, the earlier you can find the problem or do the inspection or the control, the better. The longer if you put everything at the end of line, there's a potential you're going to miss it, but also there's the potential that you're going to work, put a lot of value into a product that is wasted because actually it was non-conforming after the first process. So to create the control plan, the key document, the key input is your Process FMEA. But you will also need things like your process flow diagram. You may have control plans from similar parts, and you need to know what capability your measurement methods, your inspection methods have to make sure that you're only including things that are proven capable. And once you have defined your control plan and the checks you need, then you need to verify it using MSA. Now, this is one of the key changes with 13100. In the old days, you might have said, yeah, well, I'm only going to do that for key characteristics or whatever. If you've got something in the control plan that says, this is what I need to do to verify my process parameter or my product, as soon as you've listed that in your control plan, the question is, well, is it capable? So if you're relying on a temperature process parameter measurement, is the way you measure that temperature, is that capable? If you're going to say, well, I'm going to use a vernier at op 10 to do a first off check, and I've got that on my control plan, is it capable? So the control plan feeds the requirements for what you need to do measurement systems analysis on, whether it's visual inspection, measurement, process parameter checks, etc. So like with the FMEA, the template of the control plan, it is an industry standard, and it helps to define the information we need, and it's fairly self-explanatory. So the first few columns is, well, what's the operation? What process step am I at? And in this operation, what tools am I using? Is it a CNC machine? What tooling, what fixtures am I using? The next columns is, well, what do I check? Is it a product characteristic? Am I checking a dimension? Am I checking for damage? Or is it a process check? Am I checking for feed rates? Am I checking for temperature, etc., or pressures in the process? Then there's a detail in there. So once I know what I need to check, how do I check it? How often do I check it? And what's the frequency? So in there, you'd expect to have defined, is it a CMM? Is it a visual check? If it's a visual check, is there a standard I should be using to carry that check out? So that defines how you want the operator or the fitter to check it. How are you going to control and analyze the data? So I'm collecting all of these results, pass, fail, might be variable results. How do you want them to record it and analyze it? Like we saw yesterday, if it's variable data, it's quite easy to create trends, SPC charts, etc. If it's attribute, again, I'll be asking them to do attribute SPC. How are they supposed to look at that data in a preventive way so that we can take action before we actually make non-conformance? And if they do find something that's non-conforming, the reaction plan, what do you want them to do if they find something that's non-conforming? So those are the steps that you want to define in your control plan. So when you go back to the FMEA, we've got these prevention controls, we've got these detection controls. So there's a couple of different places these can actually fit. For the controls that are part number specific, they can go in your control plan. In some cases, they could go in your work instruction, okay? But only things that are part number specific should go in your control plan. There are other things in your FMEA that might point to more generic processes in your organization. So equipment maintenance is one, same with calibration. So the fact that you're going to maintain a CNC machine, that is not part number specific. If you're going to maintain a machine every 6 months, it doesn't matter what part you're making, that check is going to go on regardless of the part numbers going through that process. Same with calibration. There could be lots of part numbers going through that CNC. The fact that you're calibrating it is irrespective of the actual part number. So when you look back at this list, there are some things which are very much related to the part. So if you look at CMM check at op 450 detection controls, that is absolutely part number specific. When you look at preventive maintenance schedule, that is not part number specific. So we'll do a quick poll. There are 10 controls here, 5 prevention, 5 detection. Which ones would you expect to see in a control plan? So Becky, do you want to introduce the poll?
Sure. So I just opened the poll for everyone. You should see the Slido poll on the side of your screen, and you can begin submitting your votes. We'll give it about 25 seconds here for everyone to vote. Votes are starting to come in. About another 10 seconds for everyone to get in there and vote. Okay, so it looks like number 1 is 56%. Number 2 is about 14%. 3, 11%. 4 is at 21%. 5, Part X fixture, we're at 50%. Number 6, diameter check has 83%. 7, CNC spindle, 23%. 8, visual inspection, 69%. 9, 43%, and 10 has 52%.
Okay. Okay, so let's see what the answers are. So we've got number 1, operator fixture check. So because the fixture check is specific to that part number, then that could be in the control plan. You could argue it could go in a work instruction, but it's definitely part specific. The next one, CNC coolant strength check, that is not part specific. So any part that goes through the CNC process is going to benefit from making sure the coolant strength is right. So that's a generic check for the machine, not the part. Same with planned maintenance. You know, that is all about the machine. It is not part specific. Spindle alignment calibration, the same. So it's machine specific, it's not part specific. Number 5, part X feature. So part X is the part, so it's telling you it's part specific because that fixture is only used on part X. And it's got an air detect system in place, and you're checking to make sure that that system is working. The diameter check, as we said, that is absolutely part specific. Spindle alignment weekly ball bar check is the same. That's checking the machine, not the part. Visual inspection for damage, you're actually inspecting the part, so that's going to be part specific. Checking the valve test is part specific because the lab is going to check that particular part number. And the serial number check, again, you have to check the actual part to do that. So all of those you could expect to see on the control plan. You could argue with a fixture check, does that go in a work instruction? But certainly on the other ones, you would expect them to see in the control plan. So when you look at where does your information come from control plan, everything that's in red text here is repeated from information that is contained in the PFMEA. So if you have the right software, once you've created it once, and a lot of this information will actually go back to the process flow diagram. So the software I was talking about earlier called PowerWay, back in the 90s, that would have all of this information. So once you've filled in something in an earlier step, you can reuse it, which means that you're not going to get any data entry issues. So your process flow diagram can feed into the PFMEA, and your PFMEA feeds into your control plan. So with a fully populated Process FMEA, all of this information can pretty much be taken out of the Process FMEA. And that's another reason for it's really important, if you do your process FMEA with all characteristics, you can take full advantage of the automation to create your control plan. If you didn't put all your characteristics in for your process FMEA, you can create a control plan with whatever features or characteristics you put in the FMEA, but what are you going to do with everything else? You're going to have to have a different process to determine what you're going to do with the characteristics that weren't in your FMEA. So to take full advantage of software and of those systems, you've got to be consistent throughout. And if you don't put everything at the start, you've got to have supplemental processes for how you deal with other things. And that's where things get really complex and really prone to kind of fall over and bite us. So you can see there's an awful lot of information that will come from your process FMEA. So all you're really adding in is your control methods. Sometimes some of these can be in your process FMEA too, and your reaction plan. So typical things like, well, if what you want the operator to do, you want him to stop the process if he sees non-conformance. Do you want him to report to a supervisor? Those are the things you would put in a reaction plan. So he's very clear what to do if he measures something or inspects something and he finds non-conformance. Now, the other thing is, we're talking about, you would almost expect to see every measurement being included in the control plan. And again, sharp intake of breath. My God, the control plan is going to be enormous because it's going to include all of these features. But again, if you were talking to that fitter or to that machinist in the cell, when you say, well, what controls do you do? He's not going to say, yeah, well, first of all, I measure the diameter, then I measure the depth, and then I measure the roundness. In many cases, you can say, I machine it. I do a first off check with a vernier on this particular feature to make sure that's okay. And if that's okay, I run the rest. And then when I've finished, I'm just going to put it on the CMM and measure the rest of the dimensions. So in which case, all of those dimensions, whether it's 5, 10, 100, if they're all measured on the same CMM program at a certain operation, all he needs to do is say, yeah, dimensions 1 to 7, I'm going to check those on the CMM as part of my operation. So, it appears as a single line because everything to the right in the control plan is going to be the same. So it's going to ask you, well, what measurement program you're going to use, what's the frequency of measurement, what's the analysis method, what's the reaction plan. All of those are the same, irrespective of what dimension it is, because it's all been done on the same program. So, a little bit of common sense needs to come in to make sure that the control plan doesn't get out of control and is actually a manageable size. It's a simple reference document that you want to be on the shop floor so that your operator, your fitter, understands exactly what he needs to do when he's making that particular part. But it's also easy then if you're in quality, if you're a leader, you can walk around, you can go and find the control plan and see, okay, are we actually compliant with this? What results are we getting to the control plan? So as I said, you expect to see the control plan broken down into different steps. You wouldn't expect it to be particularly big for any one of those steps, because it's something that the fitter and the operator needs to be able to manage and control as part of his normal day shift. So to summarize, the control plan and the best software systems will take your FMEA and generate a lot of the control plan directly. It may need a little bit of tweaking by the team, but a lot of the information is taken directly from the Process FMEA. It should include not just the product characteristic checks, but also the process checks you want to do to make sure that you're preventing non-conformance. So including process parameters is quite different to just a list of, many inspection plans I see is basically just a list of characteristics that we need to measure on a CMM program at the end of the line. This is about the in-process checks on both product and the process parameters. It should be split into different operation numbers, so it's bite size as you go through the process. Now, where you have a shop floor system, so in Rolls-Royce we have something called MES, which is a manufacturing execution system. All of our work instructions, control plans are on there. Now, when you look in MES, you don't see the template that we have just looked at, but all of the information that's in the template is in MES and is presented to the operator when they're actually doing the operation. So as long as you can demonstrate from a software point of view that it meets the intent of the control plan template, that will be accepted. But when you come to submit your control plan as part of your PPAP pack as part of APQP, then we would expect to see the template used of that's how you would summarize it. So you've got you can provide the evidence to the customer, you can provide the evidence to yourself in the PPAP evidence pack. That's what the control plan looks like. And you can show the link from the Process FMEA to the control plan. It is a live document, it needs updating. And typically, and this is what I liked about the Powerway software that I used back in the 90s. Let's say you have an escape to the customer and you need to put in some special containment checks until you understand the root cause and you've done corrective action. So let's say you're going to put in some additional inspections at a certain operation. You'd expect to do that by adding something into the control plan, so the operator has an updated control plan where I now need to do an additional check in my operation for this thing. But to get it on the control plan in Powerway, you had to go back to the FMEA, update the FMEA profile to generate the link to the control plan to say, there's an additional check needed. You couldn't just go in the control plan and add an extra line in. And that discipline of making sure that the FMEA feeds the control plan was really good. And then to go back in when you want to stop that containment action because you've got the root cause and you've mistake-proofed it, again, you need to go back into the FMEA, update it to remove the need for that containment check. That was a really strong design point with the Powerway software. And again, and I speak from experience with this, putting checks and controls in a work instruction just ends up hiding it because not everybody refers to a work instruction every time they're doing the job. Some of these work instructions are multiple pages. They're great for training, but how often they get referred back to can be an issue. If you've got things like MES and shop floor systems, which you can't proceed unless you've actually done a check, then that is, that is good. But really, it's having the transparency of what controls you have and how they link to the risk that's generated from your FMEA is really important. Because I've gone to a lot of different businesses and say, yes, we put the FMEAs on the shop floor so our operators can see them and they can see what's important. Well, from the FMEAs that I've seen, that would just kind of it would overwhelm the poor operator because they're large documents. But it doesn't really help to summarize. So what's the risk of the step I'm doing? The document that does that is the control plan, because the control plan is fed by the risks that you've identified in your FMEA. The operators don't need to see the full FMEA. You might pull out some particular key things like any key characteristics and explain why they're key, but actually the control plan is the document say, because of the risks we've identified in the FMEA, these are the controls that we need to mitigate that. Okay, so that is control plans from FMEA. So Rudy, do we have any questions?
We have 4 questions
Okay.
to now to this block. And I think one question is already answered. Would you have a control plan per part number?
Yes.
Or a control plan for any part number?
Yeah, so let's try and come back to a fundamental. APQP stands for Advanced Product Quality Planning, where the product is a specific product part number. So everything we've talked about, FMEA, control plan, process flow diagrams, all of those are part specific, because the things you're checking are part specific. So if you have a part with 50 features on it, and each of those 50 features has a specific specification and tolerance, etc., that control plan is going to tell you how you're going to check those 50 features as you actually make it, and what you do when it's wrong, and what equipment you use, and what the specification is for each of those 50 items. If you've got another part number that has exactly the same 50 features with exactly the same tolerances, built on exactly the same process, then I'd just be surprised why you've called it a different part number, because it's identical. So the fact that you should never get 2 identical parts with identical features and identical tolerances just means that absolutely the control plan is part specific. The FMEA has to be part specific because of the same reason. The risk profile will be different because the parts will be used differently. And if it's not, and if the part has exactly the same number of features and exactly the same tolerances, why go to all of the trouble of designing a part with a different part number that's absolutely identical to a part you're already producing? So absolutely, if you take nothing else away from that question, all of these tools are part number specific.
Okay. Ian, I think the next question is already covered with your answer. Is part specific the main criteria to determine whether a control should be in a control plan?
Yeah, so absolutely. So you've got 2 choices. One is kind of controlling equipment you're using on multiple part numbers, or you may have checks on the facility itself, temperature and air conditioning. Those things aren't directly related to the part. Those are things you need to do to control the environment and the equipment capability, irrespective of the part you're making. Control plan should only include those things that you're doing when you produce that part. So if you're producing part A, these are the things you do as you're producing part A. So that is one of the key things, I think, when we showed that diagram earlier.
Okay, the next question I think is already covered with your answer just before. Do control plans need to include inspection operations? So classical inspection operations like CMM inspection?
Yeah, so on this one, you can see evaluation or measurement technique as one of the key columns in the methods. So you've got the specification on, let's see if I can. So here you've got specification, then you've got measurement technique, and just go back onto full screen. So here you would expect to see, well, it's a visual check, or it's a CMM check, or it's a micrometer check. Absolutely, we would specify that. And in some cases, you actually specify which CMM you're allowed to use. So where you have multiple CMMs in a room, maybe only certain CMMs have been proven from an MSA point of view to be acceptable for that part number. So the control plan may actually specify, in this one, I've got a Mitutoyo CMM XRC3. I can only use that one because that's the one we use to prove the MSA outcome. Because this is a tight tolerance or whatever, I can't use some of my older machines because they haven't got the capability to measure this set of features. Yeah.
Okay, Ian, a last question. I'm not sure if I understood it in the right way. Is it expected to link the PFMEA and control plan in each router?
I'm not sure what in each router means either, but
I'm also not sure. Is it expected to link the PFMEA and control plan in each router? So,
yes. So I won't go back to it now because it's very long. But this is a system of tools. So when you go through APQP, you will see that the outputs of the Process FMEA is an input to the control plan. The control plan is an input to MSA. These things are very much linked. So we should always make sure that if we change one, then what impact does it have on the processes upstream and downstream? And that's why I like the PowerWay software, because you couldn't just go and change the control plan without going and changing the PFMEA first. Those sorts of things are really good ways of enforcing the discipline of these things are linked, and they are linked because they are the same product all the way through. And you can't just go and make a change to one without understanding the impact that change has on everything else around it.
okay, Ian.
Okay.
That's it, yeah.
Yeah, and if we get any other questions in, as Rudy said earlier, we will make sure we answer those on the website.
Yeah.
Okay,
Sure.
so just to
Thanks a lot.
summarize, thanks, Rudy. Process FMEA, there are some very specific requirements in 13100, and the fact that they're called requirements means they are shall statements. They're not optional. They are hard requirements of the standard. Now, there is a caveat, and we covered it on the first webinar, unless otherwise agreed with the customer. So if you put a case forward to your customer of why you have an alternative approach which meets the intent, then these are requirements that all of us expect our external supply chain and ourselves. So the other thing to make a note of, you will see there's people on this call from Rolls-Royce, from GE, from Pratt & Whitney, from Safran. We apply these internally as well as externally. So we're not asking for anything that we aren't doing ourselves. But these are requirements. Looking at some of the chat yesterday and today, it's like, oh yeah, well we don't think there's any value in this. Well, go and agree with your customer, but these are the things. So we do expect you to have a cross-functional team. We do expect you to do it early in the APQP process. It is part number specific. All process steps, every design characteristic. We will be looking and evaluating FMEAs based on the fact that the failure modes only describe product defects, and that they're striving actions to mitigate those high severity and occurrence risks that we've seen, and that they're kept up to date. So where there are escapes, where there are internal yield problems, we would expect to see that reflected in the FMEA. So we talked software. In Rolls-Royce, we use something called XFMEA, and it's a very flexible piece of software, but I think we also have to acknowledge that because it's a flexible piece of software, you do need people who can almost program it to give you the results you want. The benefit of it being flexible is in Rolls-Royce, we've actually developed it so we can have an FMEA library created in XFMEA that allows us to combine that with a characteristics matrix to generate the shell FMEAs really, really simply. And also, through pressing a few buttons, you can get your XFMEA to generate the control plan from what's in the FMEA. So it doesn't do that off the shelf, is the care point. It had to be configured that way by Rolls-Royce experts to be able to do that. So the plus side, it's really, really flexible. The downside is it doesn't come out of the box and do that. Now, I looked at a study from a couple of years ago that kind of described a lot of different softwares they're using. So, some people, and I know there's even pockets in Rolls-Royce where some of the FMEAs were done on Excel and they're still in Excel today. There's a company, Datalyzer, that sells an integrated APQP style software. FMEA Pro, PowerWay, I've mentioned. I'm not sure if that's still the name of the organization or if it's changed. And something called FMEA. So what I'd be interested to say, out of those 1 to 6, for the people on the call, what are you using? Are you using any of those today? Or 7, are there something else? And if it is something else, maybe using the chat function, you might want to share that, because one of the questions we get a lot about is what software do people use? And if you're prepared to recommend it using the chat function, we'll collate it and we'll make it available. But we'd be really interested to know what people are using for their process FMEAs and control plans. Okay. Becky, have you started? Is this a poll or is this a chat?
This is a poll, so the poll is open. We have 125 votes so far, so we can give it a few more seconds.
Okay.
I also see some responses coming in through the chat, but 152 votes, maybe a few more seconds here. It looks like Excel is in the lead. This is like calling a pony race. Excel right now has 92%.
Okay.
Datalyzer has 2%. XFMEA has 2%. FMEA Pro has 1%. PowerWay is 0. PQFMA 1%, and other shows as 6%.
Okay.
And based on what's in the chat, I see something called Skill FMEA Pro. There's one called QDA9 Solutions. There's one that says we're switching over to Datalyzer.
Okay.
So, but yeah, Excel still has 93%. We have 210 votes right now.
Okay. And that's really interesting, because I think that the study that I was reading from, I think it was 2017 and 18, that also put Excel way out in front of the software that most people are using to create and manage process FMEAs. And it's readily available. It's easy to use, but it's quite time consuming. And because it doesn't link easily to control plans and process flow diagrams and stuff, it can therefore not be the most efficient way of managing this amount of data. So with all of the other tools, absolutely, there are things you need to invest in, there are things you need to pay for, they're not free. But spending some time on looking at a system that is an integrated system that can do your design FMEAs, your process FMEAs, your process flow diagrams, your control plans, will definitely be there'll definitely be a business case to invest in that. Whether we like it or not, APQP PPAP is coming. It's been flowed down to Rolls-Royce and all of the engine manufacturers from our customers, Boeing, Airbus, Bombardier, Gulfstream. APQP is becoming an industry way of managing new product introduction and changes. It will, it'll be the cost of doing business. Like within the automotive industry, you couldn't say to Ford or GM, yeah, I'm not doing that, because you wouldn't get the contract and you wouldn't be an approved supplier. This stuff is coming. It's even more important for us. We explained at the start that the consequences of poor quality in aerospace can be really, really serious. We make our parts for 20 to 30 years. If we can get rid of non-conformance, the amount of money we can save, the amount of disruption we save, the amount of emotion, as well as the safety impact of that is huge. We have to get really good at this. Resources are always going to be extremely tight in terms of engineering time and how much time we have to do this. With the right software, using reference FMEAs, getting the team skilled with doing FMEAs and control plans will mean that it'll take a lot less time than where we are today. And we've all been through that journey of having a team of people sitting in a room going, oh my God, do you mean every step, every characteristic is too much, is too big, we're gonna drown. And every time I've been in one of those situations, at the end of the first session, I guarantee you, what people are saying on the way out is, oh, that wasn't as bad as I thought. Actually, that didn't take as much time as I was expecting it to. Actually, some good stuff come out of that. Things that we kind of wanted changed for years. Now we've got a way of justifying why we need to change the process. So that's our challenge. Not just a Rolls-Royce challenge or a GE or a Safran or Pratt & Whitney challenge. It's an aerospace challenge. We happen to be in the aero engine supply chain. For us, we are creating things that are controlled explosions every day. The whole of aerospace, whether you're making landing gear, wings, cockpit equipment, etc., are going to have to adopt this way of working. The AESQ is there to kind of help promote and accelerate how we take our supply chain on this journey. So, the fact that we've made the reference manuals all free issue is to promote the adoption of this toolkit. I know on Monday when we asked the question, there was only I think about 40% or 30% of people had read 13,004. Hope we'll encourage more people to go and read it, and the same with 13,100. Go and know what's in there, because we need to plan for being compliant to these things as we go forward. There's some fantastic training available via the SAE. It's available globally. It covers design FMEA, it covers process FMEA, it covers control plans. It even covers reference FMEAs in more detail than we've been able to cover today. But that training is there, so please, if you need training, it's there and it's available. And we do have the subject matter interest group, RM 13004. Rudy's on that team, I'm on that team. We've got about 15 people from all of the AESQ member companies. And our aim is to help the supply chain deploy these tools. And that's within our own organizations as well as the supply chain. As I said the other day, if you go on the AESQ website, if you Google it, you get onto the landing page, go under activities, that will take you to the interest groups. At the bottom of the page on the interest groups, you'll see in blue text which ones are set up and running. We're the defect prevention quality tools for APQP and PPAP interest group. Click on that, you'll get onto that website. That's where the videos for the last 3 webinars will be. That's where we will put the that's where we're going to put the PowerPoint slides that we've used on the last 3 sessions, etc. But also it's a great way to contact us. There's a link at the bottom of that page where you can email us and ask us any questions, or to suggest other ways in which we can actually support the supply chain with deployment. If you want to, if you wanted to send a page of an FMEA, it only takes a page of an FMEA to be able to evaluate it, or a control plan. If you wanted some feedback, if you were to send a representative page or 2 of an FMEA control plan to the subject matter interest group, we will take a look at it. We will provide you some feedback. So it's there as a choice if you want it. It will be treated in full confidentiality, but again, it's an offer that's there if anybody wants to take us up on that. So just to recap, last 3 webinars. Webinar 1, we looked at what does 13100 require? What are the shall statements in that we expect everybody to comply with? And we looked at a high-level approach of what does an FMEA that meets the intent of 13100 actually look like. Session 2, we went through that detail, step by step, looking at examples of what the intent of that step is and some of the common pitfalls we can get into if we're not careful. And then today we've introduced reference FMEAs, how to do a part-specific FMEA really efficiently, but also with building on best practice and building on the knowledge from other FMEAs, and how a control plan can be developed from the Process FMEA, and with the right software, almost be, press of a button, you get it for free as a result of that. So what's next? We've focused on Process FMEAs and control plans. Our subject matter interest group is in the process of developing an equivalent for design FMEAs. If you're a design make supplier, that could be of great interest to you. We're also looking at a broad Q&A session. So once these videos have been made available, and hopefully once we've done the design FMEA webinar 2, there'll be another opportunity to run just a straight Q&A where you can come in and ask any questions that might have come to mind following the series of webinars or weren't answered on the website. But it's important that this is the start of a dialogue. Really appreciate everybody taking the time to come along and engage and to ask some fantastic questions. What else would you like the subject matter interest group to do? What other materials, what else could we do to help you with it? So let us know, drop us a line, and we will try to do our best to respond to that, and it will help shape the strategy of what the subject matter interest group is going to do in the future. So I think I just want to end it with thank you for attending. Thank you to Becky. Thank you to Rudy for support. I hope you've enjoyed it. I hope you found it useful, and it's something that you can take back into your organizations and use as a way of starting the journey. And I hope we are able to keep in touch and share stories and share improvements as we go forward. So thank you very much. Thank you.